In this video, we're going to talk about estimators. An estimator is nothing more than a rule or a procedure for constructing estimates of population parameters. For example, if we want to find an estimator for the population mean, we use a sample mean, which is something you've seen a lot before in prior classes. It's just the sum of the observations divided by the number of observations. There's a few properties that we'd like to see in estimators. They are linearity, unbiasedness, consistency, and efficiency. And we'll talk a little bit about each of these. A linear estimator is one which can be expressed as a linear function of observable random variables. One simple reason for that is it offers lower computational cost, which isn't really that important today because we have lots of high-speed computers. But this was an issue back in the 50s and 60s when some of these models were first developed because these calculations had to be done by mechanical calculators. Today, a more important factor in requiring linearity is that it lets us make use of matrix algebra and linear algebra tools that allows us to do some fairly powerful manipulations of systems of equations. An estimator is said to be unbiased if the average value of the estimator equals the population parameter. In the equation here, theta hat is our estimator for some parameter, which could be the mean, it could be the variance, could be some other parameter of distribution, and we're just saying the average value of our estimator equals a true value, which means on average, it's an accurate measure of what we're trying to measure. It's neither systematically upward or downward bias, so on average, it's correct. So here's a couple of graphs that illustrate the concept. If you have an unbiased estimator and the normal curve there, or the bell curve, illustrates what the distribution of the estimator is in repeated trials. If it's unbiased, on average, the mean of that distribution of the possible estimates you might get equals the true value. If it's biased, as in the diagram on the right, the expected value of the estimator, in this case, is above the true value, which means on average, this estimator overestimates the true value of the unknown parameter. As an example of that, we talked a little bit in class about the Literary Digest poll, and in that case, the survey was based on motor vehicle registrations and on telephone numbers. Back in the 1940s, when not everybody owned a car, some households owned multiple ones, and not everyone owned a phone. So as a result, wealthier individuals tended to be oversampled, which led to an upward bias in the proportion of the vote predicted for the Republican candidate, because then, as now, Republicans on average tended to have higher incomes. Here's a little classic joke among econometricians and statisticians. 3 econometricians go hunting. They find a deer in a field. The first econometrician's fired and missed by a meter to the left. Another one fired and missed by a meter to the right. The third econometrician didn't fire, but shouted in triumph, "We got it." Think about how that might relate to the notion of unbiasedness. On average, we're getting the correct estimator, but in any given sample, it will not be equal to the true value. It's just on average, it doesn't systematically understate or overstate the value of the parameter we're trying to estimate. Consistency is a little bit different. Unbiasedness is what's referred to as a small sample property. It just means in repeated samples, your estimator is correct. Consistency is something that's referred to as a large sample property. What consistency indicates is that as the size of your sample gets larger, the distribution of the estimator converges to the population parameter. So in this case, if the true value is theta, if you have a sample of 50, you've got a pretty wide spread of the distribution. There's a fairly high probability you'll be a large amount above it or a large level below that. As a sample rises to 150, though, the estimates tend to be more closely clustered around the true value. When you get to 500 observations, it becomes even more tightly clustered around the true value. And as the sample size approaches infinity, it will collapse essentially to the single point theta hat, at least in the limit. An estimator is unbiased if the average value of the estimator in an infinite number of samples is the population parameter. It's consistent if the estimator converges to the population parameter as the sample size tends towards infinity. So those are different properties. You can have estimators that are biased but consistent. You can have estimators that are unbiased but not consistent. and you can have estimators that are consistent but are biased in any finite-sized sample. Here's an example illustrating two estimators where there may be a trade-off between unbiasedness and consistency. An unbiased estimator equals, on average, a true value, but it's possible that a consistent estimator has some bias, but it might actually have more points closer to the true value. And in some of the models we'll be looking at later in the course, there are some estimators where you might prefer a consistent estimator as long as the bias is relatively small. And in particular, because the estimator converges to the true value, in a large sample, the consistent estimator essentially will converge to the true value anyway when the sample size is large enough. Sometimes consistency is thought of as being asymptotically unbiased, even though there may be a bias in any finite size sample. In the limit, that bias will tend to zero. Another desirable property is one of efficiency, and we say that an unbiased estimator is efficient, and we only discuss efficiency in the context of unbiased estimators if the variance of the estimator is less than or equal to the variance of any other unbiased estimator. As these equations suggest, if theta hat n is an efficient estimator, its variance will be less than or equal to the variance of theta tilde sub n, where theta tilde sub n is any other unbiased estimator with a sample size n. And the variance of theta hat n is nothing more than the expected value of the square deviations of the estimator from the expected value of the estimator, that quantity squared. Essentially what this is saying is that an efficient estimator gives you the most precise estimator you can get among the class of unbiased estimators. Any other estimator will have a wider spread around the true value. Now let's talk about some specific estimators. One specific estimator that we already mentioned is a sample mean, which is just the sum of your observations over n. The sample variance is nothing more than the sum of the squared sample deviations from the mean, except notice instead of dividing by n, we're dividing by n minus 1. We'll talk about that in more detail later, but n minus 1 is what we call the degrees of freedom for the variance estimator. Just to give you a little understanding of why we divide by n minus 1, think about what the sum of the deviations of x from its mean will be. If we have a fixed number of observations, we construct the sample mean by adding them up and dividing by n, and if we know any n minus 1 observations, the nth observation will be determined by the fact that the sum of those deviations around the mean have to add up to 0. So in other words, if we have 100 observations that are measured in terms of the deviations from the sample mean, we know exactly what the 100th one has to be. So there's really only 99 out of the 100 observations that would contain unique information about the deviations. This will become clearer as we move a little bit further into the course. The sample standard deviation is just the square root of the sample variance. We measure the sample covariance as 1 over n minus 1 times the sum of the product of the deviation of x from its mean and y from its mean for each of those observations. And we get the correlation coefficient by taking the sample covariance and dividing it by the product of the sample standard deviations.